Hello again. In this video we're going to look at the system thread interface. The C++ thread class uses the system implementation to actually do the threading. There are occasions where we may need to use the system implementation directly. That's because C++ standard is designed to be available on every possible machine, and there are some systems which are a bit limited. Some of the useful things which are not available in standard C++ include setting the priority of a thread. We can say that we want a thread to have more than its usual share of processor time if it's doing something very important or which needs to be done quickly. We can also, if we're feeling public-spirited, say that we want our thread to have a lower share because it's doing something which is not very important and can wait, although people don't seem to do that very often for some reason. We can also set the affinity of a thread. It is possible to pin a thread, which means that it always runs on the same processor core. Usually the scheduler can move threads around from one core to another if it thinks that would give better performance overall. The downside for each individual thread that gets moved is that it has to store all its context and then load it up again when it starts on its new home. In finance, for example, they often have a dedicated processor core and a thread for each stock ticker, so that guarantees that the code which manages each ticker symbol is always running and always available and never has to be context switched. Each system execution thread has something called a handle. This is some data which the system uses internally. It's opaque, we don't know what type it is and we don't really care. We don't need to care. We do need it though if we're going to make calls into the implementation's API. The thread class has a member function which will return this handle. It's called native_handle. So let's try that out. We have our hello thread program again. We create a thread object with this task function as the argument. This will say hello in a different thread. We call the join function to make sure that the destructor is only called after the execution thread has completed. Otherwise our program will be abruptly terminated. We call the native handle member function on the thread, and just to see what happens again, we call it after the thread has completed execution. So let's see what happens. The native handle is this, which looks like a pointer, but a pointer to what? We don't know, and we don't need to know. After the thread has completed, the handle is now the null pointer, so that thread object does not correspond to any executing thread. With min_gw we get these numbers which might be indexes into an array. The index has the value 0 after the thread has completed, and again that suggests that the thread object is not connected to any execution thread. Each execution thread has a thread identifier, which again is used internally by the implementation. This ID is guaranteed to be unique, so if two thread identifiers are equal, two execution threads have the same ID, then the thread objects which represent those threads are the same object. They have the same address in memory. So you could use this for storing thread objects in associative containers. You could have, for example, a map where the key is the thread identifier and the value is the thread object. There is one caution here, that the IDs can be reused. If you have a thread which completes and then a new thread starts up, this new thread could use the ID that the earlier thread had. There is a member function for returning this, getID. This will return the identifier of the execution thread for this object. There's also this function, this_thread getID, which we can call when we're actually in a thread, and this will return the identifier for the thread which called it. We've changed our hello function slightly, so it's now going to print out the thread ID. In the main function we start off by printing the main thread's ID, so this getID function will display the identifier of the thread which called it. Then we call the member function. This will display the ID of the child thread, the hello thread, so expect that to be the same as this one. And again we see what happens when we call getID after the thread has completed execution. So we have these numbers which presumably mean something to the system, and then after execution we have ID 0. And let's see what happens with min.gw. So again, we actually get some different output here. So this corresponds to an impossible ID. And finally, something that we used to have to do through the system implementation, but we can now do through the C++ library from the C++ 11 threads implementation. We can pause a thread or make it sleep, so the thread will stop and not execute any more code for a certain duration. The function is this thread sleep for, similar to the this thread get ID, so it'll make the current thread sleep. You can't make other threads go to sleep. The argument will be one of the duration types from the chrono library. If we're using C++ 14 or later, we can use a literal as the argument, so that will represent 2 seconds. If we're using C++ 11, we have to provide a duration object. This is just a request. The thread will not actually start running again until the scheduler decides its time, so this could sleep for more than 2 seconds. And by the way, this also works with single-threaded programs. Single-threaded programs just have one thread which executes main, and you can call sleep for to make a single-threaded program sleep. You will need to include thread for that. So back to hello thread, and this time we're making it sleep before it says hello. We need to use the literal's namespace if we're using a literal, or we can just use the C++ 11 version. And the main function is exactly the same as we had first time around. So we start up, and after 2 seconds we say hello. So it's hello from the thread and goodbye from me, because that's the end of the video. I'll see you next time, but until then, keep coding.